Swayam Prabha. Digital India. Educated India.
In the last class we looked at derivation of finite element equations for 4 node tetrahedral element as a part of 3-dimensional elasticity, and as a part of that we looked at governing differential equations for 3-dimensional elasticity problems, and also we looked at in detail the finite element equations for 4 node linear element for 3-dimensional elasticity problems. In today's class let us look at 8 node solid element, which is also known as brick element, and also 20 node solid element with curved sides for solving 3-dimensional elasticity problems, and at the end we will also look at thermal pre-stress pre-strain effects, how to consider all these into account when we are solving 3-dimensional elasticity problems, or in fact any elasticity problem. And let me briefly review what we have done in the last class before we proceed with solving, or before we proceed with formulating finite element equations for 8 node solid element. So planar and axisymmetric elasticity problems that are considered in the earlier lectures are special case of general 3-dimensional elasticity theory, and the general case of 3-dimensional stress analysis shall be discussed in the next few lectures. That is what we discussed in the last class. And 3-dimensional elasticity problem involves 6 stress components and also 6 strain components. Out of these 6 stress components, the first 3 components are normal stress components, the last 3 are the shear stress components. The primary unknowns are 3 displacements along x, y, z directions, and the stress vector looks like this, the strain vector looks like this, and assuming small displacements and strains, strain displacement relationship can be written as follows. Assuming linear elastic material behavior, stresses and strains are related through this equation where C is the constitutive matrix. For isotropic material, the constitutive matrix C is as follows, where E and mu are Young's modulus and Poisson's ratio, and then before we actually derive finite element equations for any kind of element, we need to know what is potential energy functional. So in the last class we have seen potential energy functional for 3-dimensional elasticity problems looks like this, where you use strain energy, Ws is work done by the applied forces, and also we looked in detail how to calculate the strain energy by evaluating this integral, which is going to be volume integral, and work done by the applied forces is given by the traction components multiplied by displacements along that particular direction integrated over the surface on which traction is applied, and if specified concentrated forces or body forces are present, work done by the corresponding forces can also be computed in a similar manner. So, this is what we have seen in the last class, and also in last class we have seen how to calculate principal stresses once we solve for the displacements and find strains and stresses at all or the points that we are interested, and later using the 6 stress components we can calculate principal stresses for subsequent use in the failure criteria. So, with that let us start deriving finite element equations for 8 node hexahedral or brick element. This is an 8 node hexahedral element, and similar to that we already did for 4 node tetrahedral element, the element equations can easily be derived by using isoparametric mapping concept, and this actual element we are going to map it onto a parent element, which is going to be a cube having dimension 2 by 2 by 2, that is x axis goes from -1 to 1, t axis goes from -1 to 1, r axis goes from -1 to 1. So, parent element looks like this. Origin is located at the center, that is the center of this cube is located at s is equal to 0 or r is equal to 0, s is equal to 0, t is equal to 0. So, with that understanding and the dimension 3 dimensions of this cube or 3 by 3 by 2 by 2 by 2, sorry 2 by 2 by 2. So, with that understanding and with the location of origin that is at the center, we can easily find what are the coordinates of various nodes. So, for example, node 1 is located at r is equal to -1, s is equal to -1, t is equal to -1. Similarly, node 2 is located at r is equal to 1, s is equal to -1, t is equal to -1. Node 3 is located at r is equal to 1, t is equal to 1, r is equal to 1, s is equal to 1, and t is equal to 1. And node 4 is located at r is equal to -4, sorry node 4 is located at r is equal to -1, s is equal to 1, and t is equal to -1, and node 5 is located at r is equal to -1, s is equal to -1, and t is equal to 1, and node 6 is located at r is equal to 1, s is equal to -1, t is equal to 1, and node 7 is located at r, s, and t is equal to 1, and node 8 is located at r is equal to -1, s and t equal to 1. So, with that understanding we can make a note of the nodes in the parent element and their location as follows, as given here. And similar to 4 node tetrahedral element, or for that matter the early elements that we look for planar and axisymmetric elasticity problems, the trial solutions are written in terms of finite element shape functions for parent element. And trial solutions u v w, displacement component along x direction, displacement component along y direction, displacement component along z direction, can be written in terms of finite element shape functions at all the 8 nodes of this 8 node hexahedral element or 8 node brick element. The shape function the matrix consisting of finite element shape functions is denoted with letter n, and all the displacement components are put together in a vector d. So, trial solution can be written as n transpose d, and the shape functions for this 8 node hexahedral or 8 node brick element can easily be obtained using Lagrange interpolation formula that we already looked at when we are deriving shape functions for 2 dimensional elements. So, only difference is going to be we need to apply Lagrange interpolation formula in 3 dimensions. So, using Lagrange interpolation formula in 3 dimensions, the shape functions for the parent element which are required can be obtained. So, this is the parent element, and applying Lagrange interpolation formula we can write shape function corresponding to node 1 in this manner. N1 is equal to R minus R1, sorry, R minus R2, S minus S2, S minus S4, sorry, T minus T5 divided by R1 minus R2 times S1 minus S4 times T1 minus T5, and by substituting the nodal coordinates R1, R2, S1, S4, T1, T5, we get shape function corresponding to node 1 as 1 over 8 1 minus R, 1 minus S, 1 minus T. So, it is just application of Lagrange interpolation formula in 3 dimensions, and similarly shape functions for other nodes can be written. And we can write all the 8 shape functions together in a compact form in this manner, where Ni is shape function corresponding to ith node, Ri is the nodal coordinate, Ri, Si, Ti are the nodal coordinates of that particular node in the parent element coordinate system, where Ri, Si, Ti are the coordinates of ith node in the parent element. So, once we know the shape function expressions for all the 8 nodes, we can easily write the trial solutions in terms of finite element shape functions. And next is isoparametric mapping. This is similar to the earlier elements that we have seen, except there are 8 nodes. So, 8 shape functions and the corresponding x coordinates of all the 8 nodes. X is equal to n1 x1 plus n2 x2 plus n3 x3, so on, n8 x8, all this we can put together in a matrix and vector form in this manner. Similarly, y can be written in terms of finite element shape functions and the nodal coordinates of all the nodal y coordinates of all 8 nodes. Similarly, z can be written in terms of finite element shape functions and z coordinate of all the 8 nodes. Once we have this, we can easily derive, since all the shape functions are functions of RST, we can easily find what is partial derivative of x with respect to RST, similarly y with respect to RST, and z with respect to RST for subsequent calculations for strains. Strain displacement relation, the partial derivatives of u, v, w are evaluated using chain rule, as was done for 4 node tetrahedral element. For example, derivatives of u are written as follows. This equation gives partial derivatives of displacement component along x direction with respect to r s t, and partial derivatives of displacement along x direction with respect to x y z. So, this is where we require to find partial derivatives of x with respect to r s t, y with respect to r s t, z with respect to r s t. Once we know partial derivatives of x with respect to r s t, y with respect to r s t, and z with respect to r s t, we can easily find what is J, which is Jacobian matrix, and the inverse relation this is the inverse relation. Derivatives of u, that is displacement component along x direction with respect to x y z, can be computed by inverting matrix J. So, this gives the inverse relationship of the previous equation, and here substituting partial derivatives of u with respect to r s t. We know u in terms of finite element shape functions. So, we can, since finite element shape functions are in terms of r s t, we can easily take derivatives of finite element shape functions with respect to r s t. So, we can easily find what is partial derivative of u with respect to r s t in terms of finite element shape functions. So, substituting all that information, we get this, and which can be compactly written using bux, buy, buz. So, this gives partial derivatives of displacements along x, displacement along x direction with respect to x y z. Similar relations can also be developed for partial derivatives of displacement component along y direction, z direction with respect to x y z. So, these two equations gives derivatives of v with respect to x y z, w with respect to x y z, which is compactly written in terms of bvx, bvy, bvz, bwx, bwy, bwz. So, we now obtained all the quantities that are required for calculation of strains. Strains requires derivatives of displacement components with respect to x, y, z. So, using the definition of strain vector, the strains can now be expressed in terms of nodal displacements by choosing appropriate rows from the above matrices. First definition of strain: epsilon x is equal to partial derivative of u with respect to x, epsilon y is equal to partial derivative of v with respect to y, epsilon z is equal to partial derivative of w with respect to z. Similarly, gamma xy, partial derivative of u with respect to y plus partial derivative of v with respect to x, gamma yz, partial derivative of v with respect to z, partial derivative of w with respect to y, gamma zx, partial derivative of w with respect to x, partial derivative of u with respect to z. This entire vector can be written or rearranged in the manner that is shown on the right hand side of the equation. Once we have the right hand side, we can now replace that with appropriate rows in the equations that we have already derived in terms of b's: bux, buy, buz, bvx, bvy, bvz, bwx, bwy, bwz in this manner, and which can be compactly written as B transpose D, where B is strain displacement matrix. So, this is how we can calculate the strains for this 8 node hexahedral element. So, now we are ready to actually get the element stiffness matrix. So, by substituting strains into strain energy expression, we can get this, where K is the element stiffness matrix. We can see here that for this 8 node hexahedral element, strain displacement matrix B is not a constant. So, we need to adopt numerical integration scheme to evaluate this element stiffness matrix. The individual terms in K matrix must be evaluated using numerical integration technique like Gaussian quadrature. So, now let us briefly look at numerical integration in 3 dimensions, which helps us to evaluate this kind of integrals. The product Gauss integration formulas for 3 dimensional problems can be written in a manner similar to that for 2 dimension, except that we need to do whatever we have done for 2 dimension, we need to extend it by one more dimension to get integration formulas for 3 dimensional case. So, integral something like this, I is equal to minus 1 to 1 minus 1 to 1 minus 1 to 1 integral f dr ds dt. So, basically stiffness matrix, element stiffness matrix, the components of element stiffness matrix usually will be in this form. So, this can be evaluated or numerically approximated using Gaussian quadrature, the way it is shown on the right hand side of the equation, where Ri, Si, Ti are Gauss points and Wi, Wj, Wk are the weights. So, Ri, Si, Ti Gauss points, L, M, N or number of integration points along R direction, S direction, T direction. These need not necessarily be same, depending on the order of polynomial along R, S and T directions. We can select different values for L, M and N, and the total number of integration points are going to be L times M times N, and Wi, Wj, Wk are the weights, Gauss weights, and F as a function of Ri, Si, Ti is value of integrand at point Ri, Si and Ti. And now the important thing is how to know the locations and weights, the locations of Gauss points in each direction, and corresponding weights are same as those for 1 dimensional problems that we are already familiar with. So, let us look at the Gauss weights and corresponding weights at each Gauss point and corresponding locations of the Gauss points if we try to adopt 2 by 2 by 2 integration. That is, if we select 2 number of integration points along S direction, R direction, 2 number of integration points along S direction, 2 integration points along T direction, that is 2 by 2 by 2, 2 by 2 by 2 by 2 integration formula. Two by 2 by 2 integration formula. The point locations integration, there are going to be 8 integration points, 2 times 2 times 2 is 8. So, there are going to be 8 integration points. The corresponding locations of these integration points, what is the R coordinate, S coordinate, T coordinate, and the weight at each of these integration points is indicated in the table, and this is just arrived at using the information that we have already for 1 dimensional problems, which we looked at in the earlier lectures. So, this is how we can evaluate numerical integration in 3 dimensions, 3 dimensional for 3 dimensional case, and using this kind of formula we can evaluate individual terms in the element stiffness matrix. Equivalent nodal forces, this is similar to 4 node tetrahedral element, let Tx, Ty, Tz be the components of traction surface forces that are applied along x, y, z directions. So, work done by these forces are given by the traction components multiplied by the corresponding displacement components integrated over the surface on which the forces are applied, and this can be further written compactly in the manner that is shown on the right hand side of the equation, d transpose qt, where qt is equivalent nodal load vector. And this is going to be a surface integral for 8 node hexahedral element. So, the integrations can be performed numerically similar to that we already looked at in the earlier classes for evaluating integrals in 2 dimensions, and similar kind of expressions can be written for other kinds of applied forces, body forces and other forces. So, we looked at how to get element stiffness matrix for 8 node hexahedral element, and also how to evaluate equivalent nodal force vectors. So, with this we can actually assemble element stiffness matrix for each of the elements in the finite element discretization for that particular, for the particular 3 dimensional elasticity problem, and we can also assemble the equivalent nodal load vectors for the particular loading, and then we can assemble using these element equations, we can assemble global equations, and applying appropriate boundary conditions we can get the reduced equation system, solve for the unknown displacements, and subsequently we can, using strain displacement matrix, we can solve for strains and stresses, and then we can do all kinds of post processing of stresses using principal stresses that we discussed in the last class. So, all that procedure is similar to that we have already have seen for 2 dimensional problems. So, now let us look at the other element, that is 20 node isoparametric solid element. So, before we proceed, let me summarize. This 4 node tetrahedral element is counterpart of 3 node linear triangular element, and 8 node hexahedral element is counterpart of 4 node element for 2 dimensional problems, and 20 noded isoparametric element is going to be counterpart of 8 node serendipity element. So, this is a 20 node isoparametric element with curved edges, and similar to that we have seen so far, element equations are derived using isoparametric mapping concept. So, for that we require a parent element. Parent element for this 20 node element looks like this, where center of element is located at the center of the cube, which is having dimensions 2 by 2 by 2, and with that understanding we can easily write the locations of all the nodes with respect to the parent coordinate system, and once we have that information we can write the trial solution written in terms of finite element shape functions is similar, this equation is similar to that we have seen earlier, except that number of nodes increased. Matrix consisting of finite element shape functions is denoted with letter n, and the displacement components at all the nodes is denoted with letter d. So, it is compactly written as n transpose d. The shape functions for the parent element can be obtained using similar kinds of procedures that we adopted for obtaining shape functions for 8 node serendipity element for 2 dimensional problems. So, here directly the expressions are given. Shape functions for parent element are of serendipity type and can be written as follows for corner nodes. So, we cannot write one general expression similar to that we have done for 8 node hexahedral element. Here the shape functions expressions are going to be different, or they look different for corner nodes, mid side nodes. So, we need to write those separately. So, for corner nodes, that is nodes 1, 3, 5, 7, 13, 15, 17, 19 for the node numbering that is given or that is shown in the figure there. So, for corner nodes the shape function expression looks like this. Where Ri, Si, Ti are the coordinates of node in the parent element. For mid side nodes, that is nodes which are located at are nodes for whose S coordinate is 0, Ri the nodal coordinate, R coordinate of that particular node or mid side nodes whose R coordinate is plus or minus 1, whose T coordinate is plus or minus 1, S coordinate is 0, such nodes that is node 4, 8, 16, 20. For these nodes the shape function expression is given by this. Similarly, for mid side nodes whose T coordinate is 0 and R coordinate is plus or minus 1, S coordinate is plus or minus 1, that is nodes 9, 10, 11, 12, shape function expression is given by this. And for mid side nodes whose R coordinate is 0, S coordinate, T coordinate are plus or minus 1, that is nodes 2, 6, 14, 18 is given by this. Please note that these expressions are valid only for the node numbering that is shown in the figure here, and if you adopt a different node numbering then these expressions are going to be different. And again these expressions are developed using the serendipity similar, the procedure that we adopted similar to that when we are deriving shape functions for serendipity element, 8 node serendipity element for 2 dimensional problems. So, once we got all the finite element shape function expressions, we can write isoparametric mapping for 20 noded element similar to that we did for earlier elements, except that the dimensions of these vectors are going to be increased because there are 20 nodes. So, once we have isoparametric mapping expressions, we can easily find partial derivative of x with respect to RST, y with respect to RST, z with respect to RST for subsequent use in strain displacement relations. So, strain displacement relationship, partial derivatives of u, v, w are evaluated using chain rule as was done for tetrahedral or hexahedral element, and these equations looks or these equations are similar to that we have seen for other elements earlier, except that some of the dimensions may be different, where J is Jacobian matrix and the inverse relation is given by this. So, this equation gives derivatives of u with respect to x, y, z which can be compactly written similar to that what we did for 8 node hexahedral element, except that the dimensions of matrices are going to be more. So, similar derivatives for u and w can be written or expressed as follows. So, once we have all this information using the definitions of strains in terms of displacements, we can easily substitute these quantities and get the strain displacement matrix or strain displacement relationship for 20 noded isoparametric element. Strains now can be expressed in terms of nodal displacements by choosing appropriate rows from the above matrices. Strain definition in terms of displacement components, which can be rearranged as shown on the right hand side. So, now plugging in or selecting the appropriate rows from the previous equations, we can get this. So, basically all these details are similar to that we already looked for 8 node hexahedral element, except that dimensions of matrices and vectors are going to be longer. So, strain can be compactly written as B transpose D. Substituting this definition and the strain energy expression, we get element stiffness matrix, where K is element stiffness matrix, defined like this. The individual terms in K matrix must be evaluated using numerical integration like Gaussian quadrature, because B matrix is not a constant. And only thing is size of the K matrix you need to keep in mind. Here there are 3 degrees of freedom at each node, there are 20 nodes. So, size of stiffness matrix is going to be 60 by 60, because there are 20 nodes and at each node there are 3 degrees of freedom. So, we got element stiffness matrix. Next is equivalent nodal force vector, or before we proceed there, numerical integrations. The previous element stiffness matrix we need to evaluate using numerical integration. So, quickly let us go through numerical integration in 3 dimension, similar to that we already looked for 8 node hexahedral element. So, product Gauss integration formulas for 3 dimensions can be written in a manner similar to that for 2 dimensions, and so each component of element stiffness matrix can be evaluated using this formula, where definitions of various quantities are given. This is just for completeness. I am showing you numerical integration 3 dimensions again. And for 2 by 2 by 2 integration, the coordinates and weights of various integration points are given here. So, adopting this kind of formula, we can evaluate each component of element stiffness matrix. So, next is equivalent nodal force vector. If t x, t y, t z are the components of tractions along x, y, z directions, what done is given by this integral, which can be compactly written as d transpose q t, where q is the equivalent nodal load vector, and integration must be performed to evaluate this numerically, and similar expressions can be written for other kinds of forces acting on other faces. So, once again, element stiffness matrix for 20 noded isoparametric element is going to be 60 by 60 from each element, and also equivalent nodal force vector is going to be 20 length 20, that is vector is going to have 20 components. So, procedure wise the dimensions of matrices and vectors are going to be longer, other than that conceptually the procedure for assembling the element matrices and vectors and getting the global equation system and applying the essential boundary conditions and getting the reduced equation system and solving for the unknown nodal displacements and calculations of strains, stresses, all those details are similar to that for the problems that we looked at earlier. So, now let us look at pre-stressing, initial strains and thermal effects, how to handle this. A uniform temperature change in an elastic solid produces uniform expansion, that we already know. Strain associated with temperature change delta T is given by this. Only normal components will be non-zero, shear components are going to be 0. So, this is a strain associated with temperature change of delta T in an elastic solid, and this for plane stress and plane strain case is given by this plane stress and for plane strain case, and in all these equations alpha is coefficient of thermal expansion and delta T is the change in temperature and nu is the Poisson's ratio. So, this is how we can calculate strain associated with temperature change. And pre-stressing implies presence of some unknown initial stress in the body. Basically, that is what we are going to do when we are actually analyzing pre-stress concrete. So, pre-stressing implies presence of some unknown initial stress in the body. The stresses, the corresponding stresses are pre-stressing, the stresses corresponding to this pre-stress are denoted with sigma naught, and taking care of these pre-stresses, the stress strain relationship can be written like this. The actual stress that is developed in the body is going to be dependent only on the strains, excluding the strains that are associated with change in the temperature or initial strains. So, stresses are going to be given by C times epsilon minus epsilon naught plus initial stresses sigma naught, where C is the constitutive matrix. So, this is how stresses in a body subjected to temperature change or initial strains can be calculated. So, using this definition, strain energy in the presence of initial stresses and strains can be written like this. So, only difference here is instead of epsilon, epsilon minus epsilon naught is used in the first expression, second one is coming from the work done by the or the strain energy, sorry, the strain energy because of developed strains in addition to initial strains and initial stresses. So, this can be further simplified and we get these all terms, and we know that by differentiating strain energy we get element equations. Since element equations are obtained by differentiating strain energy with respect to the nodal variables, which are going to be nodal displacements, the constant terms will not have any influence and can be dropped. So, whatever constant terms are there in the previous equation, they will all dropped off when we take derivatives with respect to the nodal displacements or nodal variables. So, finally, we are going to get this one. So, we can before we do differentiation we can remove the constant terms, or we can take derivatives of constant terms, automatically they are going to be 0. So, by taking the strain energy expression without constant terms, before we proceed, actually we need to substitute the definitions of strain, or strain in terms, we need to express strain in terms of nodal displacements. So, finite element approximation of nodal displacements n transpose d, strains b transpose d, substituting this into the previous equation in which constant terms are avoided, we get this, which can be written in a matrix and vector form in this manner, where each of the terms are defined like this. Q epsilon naught, q sigma naught are due to initial strains, due to the presence of initial strains or stresses. So, element equations are obtained by differentiating the previous equation of strain energy u with respect to the nodal displacements or nodal parameters, and we get this equation. And you can see this equation, and it can be noticed that stiffness matrix K is similar to that we already looked at in the earlier case. In earlier cases, our stiffness matrix is same as before, except that the presence of initial strains and stresses or temperature changes do not have any effect on the element stiffness matrix. That is what we can notice, and also all these effects, that is initial strains or stresses and temperature changes are incorporated into the nodal force vectors or nodal load vectors. So, we can proceed similar to that we already discussed for other kinds of elements, for various kinds of elements that we discussed during this lecture. Similar to that, what we can do is, with this definition of element stiffness matrix and force vectors, nodal load vectors, we can assemble in case initial strains or stresses are present, or if there is change in temperature, we can assemble the element equations as usual, and also the equivalent nodal load vectors can be assembled using the equations that we just saw, that we have just seen, the equation using the q epsilon naught q sigma naught equations and get the element equations, and using nodal connectivity we can assemble the global equations and apply appropriate essential boundary conditions and solve for the nodal displacements and do all kinds of post processing. So, this completes 3-dimensional elasticity problems. So, after solving for nodal displacements, element stresses can be calculated using the last equation that is shown.